Hi everyone, thank you for being here. I'm Aizierjiang from the George Washington University. Today I'd like to talk about a very practical tension in federated learning. The methods that fix its biggest statistical problem tend to double its biggest systems cost. Our work, which we call MB-LSGD, Momentum Buffered Local Stochastic Gradient Descent, shows that you don't have to make that trade. We correct client drift while sending exactly the same bytes per round as plain federated AVG. Here is the roadmap for the next 20 minutes or so. I will first spend a few minutes on why client drift is a problem and why the existing fixes are expensive. Then I will walk you through our method. The core idea fits in one equation, so don't worry about that. After that, I will briefly summarize what we can prove about it, and then spend the rest of the time on experiments on CIFAR10 and TinyImageNet, including the cases where things get subtle. Let's dive in. So first, why does this problem matter? In federated learning, we want to train a single global model over M clients, phones, hospitals, edge devices without ever moving their raw data. Formally, we minimize the average of the local objectives, where each client's objective is just its expected loss on its own data. That's the equation you see here. The defining systems cost, like defining the constraints in this setting, is what communication is far more expensive than local computation. The classic answer is local stochastic gradient descent, local SGD, better known as FedAvg. Instead of synchronizing after every gradient step, each client runs key local steps, and only then does the server average the models. That immediately buys you a factor of key fewer communication rounds. And this is the catch at the bottom of the slide, this efficiency degrades exactly where federated learning is needed most. When client data is heterogeneous, what we call non-IID. And that's essentially always the case in practice. So what actually goes wrong? When data is non-IID, each client's local objective is different from the global one. During those key local steps, every client is quietly working toward its own local optimum rather than the global one. This is what the literature calls client drift, and the equation here summarizes it. It's the accumulated gap between local and global gradients along the local trajectory. Two things to note here. First, the drift grows with key. The more local work you do, the worse it gets. And with the heterogeneity level, which we measure by constant g-square. Second, the more importantly, it produces a bias that does not vanish over runs unless you decay the learning rate towards zero. Non-IID concrete. This is concretely meaning that the actual label distribution we use in our experiments, a Dirichlet partition with concentration 0.1 over 100 clients. Most clients see only a couple of classes. This is the regime we care about. Of course, we are not the first to attack client drift. The table gives you the landscape. The gold standard is scaffold, which corrects drift with control variates, and it works. But the client has to ship its control variate along with the model, which roughly doubles the per round payload. Regularization methods like FedAvg and FedAvg keep the payload at one model, but they bring sensitive hyperparameters and extra compute. Momentum-based methods like FedCM, MEME, STEM, FedAvg can need server-side statistics, and as we will see later, some of them become unstable when only a few clients participate each round. FedDC tracks the local global gap with an auxiliary variable, and ProgSkip gets to Zero-Payload through randomized communication. So the question we ask is the one at the bottom. Can we get the scaffold style drift correction while sending 0 extra bytes? Nothing beyond the model FedAvg already sends. Our answer is yes, at least in our experiment, and comes with 3 contributions. First, drift correction at 0 payload. MB-LSGD runs on exactly FedAvg's communication budget. No auxiliary state ever crosses the network. Second, we identified a fix, what we call the half-staff bias. If you build a drift estimator natively as an exponential moving average of what you observe, it converges to only half of the correction you need. Our additive update rule eliminates that bias. And third, we prove a convergence bound of order 1 over the square root of mkr for smooth non-convex objectives, and the bound explicitly couples the buffer rate alpha with the partition rate p, which turns out to be exactly the guidance you need to tune this method in practice. So let's look at how it actually works. Start from a thought experiment. If a client could add a correction term C_m to its local gradient so that in expectation it follows the global gradient, what would that term be? The answer is immediate, and it's the boxed equation. The ideal correction is the global gradient minus the local gradient. If every client had this, the local updates would match the centralized direction in expectation, no matter how heterogeneous the data is. Heterogeneity would simply stop mattering. The problem, of course, is that no client knows the global gradient, and transmitting everyone's gradients to compute it would blow up exactly the bandwidth and privacy budget we are trying to protect. So here is the MB-LSGD idea in one sentence. Each client maintains a local drift, like local drift buffer, U_r to the m, that estimates this ideal correction and adds it to every one of its key local steps. The buffer stays fixed within a round and acts like a control variable steering the trajectory. The whole question now becomes, how do we update this buffer without communicating anything extra? And here is the key observation of the paper. The aggregated model that the server broadcasts anyway, W_r+1, already encodes global gradient information. We just have to read it out. Concretely, we define 2 pseudo gradients. The global effective step is how far the global model moved this around, divided by μk. The local effective step is the same thing for the client's own model. Notice that everything in these formulas is already sitting in the client's memory. It knows last round's model, it receives the new global model anyway, and it obviously knows its own final iterate. So both quantities are computable locally with no extra communication whatsoever. Under full participation, The global pseudo gradient is exactly the average of the local ones. That's an identity, not an approximation. And for a reasonably small learning rate, these pseudo gradients track the true gradients at the start of the round. The global one approximates the global gradient, and the local one approximates the local gradient plus the buffer that was applied during the round. Subtract the two, and look what you get here. The bottom box here we mentioned, the difference is the ideal correction minus the current buffer. In other words, it's precisely the part of the drift buffer that has failed to correct so far. That's the perfect error signal. And given that error signal, the update rule is almost embarrassingly simple. Left box, as you can see here, is the new buffer equals old buffer plus alpha times the residual. Just accumulate the residual drift scaled by a buffer rate alpha between 0 and 1. But there is a subtlety here, and it's one of our main contributions. You might be tempted to do the seemingly natural thing instead. The right box, an exponential moving average of the buffer you applied or you observed. Difference. An exponential moving average of the observed differences. Here is the trap. The local pseudo gradient already contains buffer you applied, and if you work out the stationary point of EMA version, you find it satisfies 2 star equals the ideal correction. So the naive estimator converges to exactly half of the correction you need. It permanently undercorrects. Our additive rule doesn't have this problem. It's stationary. Condition recovers the full correction, at least under a linear approximation of the trajectories. One more word on alpha is that setting it to 1 tries to fix the whole observed error in a single round, while smaller values smooth the estimate over rounds and are much more robust to stochastic noise. Values above 1 overcorrect and oscillate. So we never use them. The update is related to client-side momentum, like the work by Cheng and his colleagues, and the author's colleagues studied that before. And what's new here is the explicit coupling between alpha and the participation rate, and the stability story under high noise. Let me put the whole algorithm on one side. Now with partial participation, which is how this would actually run, 4 steps here. 1. The server samples a fraction p of the client and broadcasts the current model. 2. Each sampled client runs its key-corrected local steps and sends back only its model. I want to emphasize this. The payload is one model, exactly like FedAvg. 3. The server averages business as 0. 4. Each participating client updates its buffer locally using the pseudo gradient residual. Everyone else simply keeps their buffer unchanged. 2 remarks to be mentioned here is that buffer starts at 0, so the first round is plain FedAvg, and under partial participation, a given client only refreshes its buffer about once every 1 divided by P runs, and that staleness is not a detail. It tightens how aggressive you can be with alpha, and our theory makes that precise, which brings me to the analysis. So what can we actually prove about this? I'll keep it to 2 slides here. The analysis rests on standard assumptions. L smoothness, unbiased stochastic gradients with variance like delta square, and bounded heterogeneity G square, and it tracks one central quantity, the buffer error E R to M, the gap between each client's buffer and the ideal correction. The first lemma bounds how far local iterates wander from the round start model. In vanilla local stochastic gradient descent, that deviation is governed by the heterogeneity G square. Here, and this is the point I want you to take away from this slide, is G square does not appear in the round at all. Does not appear in the bound at all. The deviation is driven by the stochastic noise and by the buffer error instead. So if the buffers are accurate, heterogeneity simply drops out of the local dynamics. The second lemma shows the buffer do become accurate. The buffer error contracts geometrically with factor 1 minus alpha p over 2 plus lower order noise terms. Notice how the contraction speed is exactly the product of the buffer rate and the participation rate. This is where the two get coupled, and that coupling propagates into the main theorem. Combining the two lemmas through a Lyapunov potential, objective value plus scaled buffer error gives our main theorem. The bound has 4 terms: the usual initialization term, a variance term, a heterogeneity term, and a tracking term that depends on alpha and p. 3 consequences. First, with the standard step size choice, the rate is order 1 over the square root of mkr. That matches centralized mini batch SGD up to constants, and it matches scaffold's order without transmitting any control variates. Second, heterogeneity decoupling. Look at where G square sits. It's divided by R, so it's a transient term. It slows down the early phase while the buffers are still learning their local biases, but it does not set the asymptotic error floor. For FedAvg, it does. That's the qualitative difference. Third, the alpha p coupling gives concrete tuning advice. Optimizing the bound suggests alpha on the order of 1 over square root of k, and in particular, under high noise and sparse participation, you want alpha strictly below 1. With alpha equal to 1, the buffer swallows the stochastic noise of every single observation. Keep this in mind because it will explain what we see in the ablations. So much for the theory. Does it hold up in practice? Our setup follows the standard non-IID benchmark protocol. 2 tasks here. CFAR 10 with a simple CNN and tiny ImageNet, 200 classes with a ResNet 18. In both cases, we partition the data over 100 clients with a Dirichlet concentration of 0.1, which is the strongly skewed distribution I showed you earlier, we run 200 communication rounds, sampling 10% of clients per round. Each selected client does 5 local epochs with batch size 256, learning rate 0.01, and gradient clipping at norm thread. We compare against FedAvg, Scaffold, FedCM, and ProgSkip, and one accounting note, so the communication numbers are unambiguous, is that we count dense 32-bit payloads with no compression, and Scaffold uploads both the model and its control variant updates, so it pays double per round. Here are the CIFAR 10 results. Let me upfront about the speed column. ProgSkip is the first to reach 60% accuracy at around 144. FedAvg follows at 148 to 147. And we get there at 159. Scaffold at 168. So we are not the fastest out of gate. But look at the peak versus final columns, because that's the interesting story. Every other stable method peaks and then degrades. ProgSkip peaks at 63.1 and ends at 58.3. FedAvg drops about 3 points, Scaffold about 2.5. MB-LSGD is the only method whose final accuracy equals its peak, 61.67%. No late stage decay at all. And that makes it the best final accuracy on the slide. In real deployment, you usually live with the model you have at the end, not at the cherry-picked peak. And the coast column here, we do this with 8.57 gigabytes of total upload, identical to FedAvg, half of Scaffold's 17.13. You will also notice FedCM, it diverged under this setting, peaking at 30% and collapsing to 11. I will come back to why. On the larger tasks, the gap opens up and drift correction really pays off. MB-LSGD reaches the highest peak accuracy, 48.37%, ahead of Scaffold at 47.49. And we do it at half Scaffold's bandwidth, 90 gigabytes versus 180. The zero-payload baselines without drift correction, FedAvg and ProgSkip plateau around 40 to 41%, so we are about 7.5 points above FedAvg at identical communication cost. FedCM again diverged. The accuracy versus bytes view on the right makes the efficiency picture very visual. Our curve sits clearly above Scaffold because every byte simply buys more accuracy. And now let me translate those bytes into time. Since this is a systems audience, our main focus is based on over 200 rounds that we have 8.56 gigabytes on CIFAR 10 and 90.17 gigabytes on Tiny ImageNet relative to Scaffold, a 50% reduction at matched or better accuracy. Modeling around time as compute plus communication, our corrected update adds literally 1 vector addition per local step. So compute time matches FedAvg, and at matched compression, Scaffold's communication time is roughly twice ours. for the TinyImageNet workload, about 45 megabytes per client per round, around 451 megabytes across the 10 sampled clients. That means in the communication bound regime typical of cross-silo and edge deployments, say 10 to 100 megabytes per second of uplink. The end-to-end completion time improvement over scaffold approaches a factor of 2. And against FedAvg and ProcSkip, we coast essentially the same time per round while ending up far more accurate. Now the ablations on TinyImageNet, and I want to be fully transparent here because there is a very interesting discovery here. Like panel A, the buffer rate in independent ablation runs, the small buffer rate alpha equals to 0.1 converges stably to about 47%, while alpha equals to 0.5 and alpha equals to 1.0 degrade sharply down in the mid-20s. That's exactly the small alpha regime our theory favors. Remember, alpha of order 1 over root k. Our main experiment did score 48.37 at alpha equals to 1, but we regard that as a lucky outlier under the very high run-to-run variance of this regime. So our practical recommendation is clear. Use a small alpha, not 1. And panel B here mainly describes the heterogeneity at the extreme Dirichlet 0.01. The run gets stuck near 10%, and at 0.1 we reached the 48 we saw, and at the milder 0.5 this run reaches 34%. The early phase slowdown as heterogeneity grows is exactly what the transient G-square term predicts. And panel C here is the participation, which is non-monotone. 5% gives 27.6, 20% gives 27.2, while the default 10% run reached 48. That looks odd. Shouldn't more clients help? And it deserves an explanation, which I'll sketch on the next slide and detail in the backup. First, why does FedSIAM diverge while we don't? FedSIAM accumulates a global momentum direction across rounds. Under strong heterogeneity and 10% sampling, that accumulated direction goes stale and biased. Our buffer instead tracks the current round local versus global drift signal. It never accumulates stale global directions, so it avoids that failure mode by construction. Second, limitations honestly stated. MB-LSGD needs order D extra memory per client for the buffer, the same footprint as scaffold and MAME. Fine if a client can hold one extra model copy, a real constraint on tiny devices. The method is stateful. So in cross-device fleets where a client may show up only once, you'd need a stable buffer policy, periodic reset, warm restart, which we leave to future work. And during the transient phase, while buffers are still learning, the behavior is close to plain local SGD. As for the participation puzzle from the last slide, the short version is that with mu alpha held fixed across the sweep, the step size condition and the tracking error, like from the short version is that with eta alpha held fixed across the sweep, the step size condition and the tracking error floor both shift with P. Retune the hyperparameters for each participation level and the dependence becomes monotone again. The full argument is in the backup. Let me wrap up. 4 things I'd like you to remember. 1. Client drift can be corrected using only the information FedAvg already communicates. The aggregated model itself adds 0 additional payload. 2. If you build that estimator naively as an EMA, you silently lose half the correction. The additive rule fixes it. 3. We prove the 1/root MKR rate with an explicit coupling between buffer rate and participation rate and heterogeneity demoted to a transient term. 4. Empirically, the highest final accuracy among all stable baselines on both benchmarks at half of scaffold's bandwidth, which approaches a 2 times completion time whenever you are communication bound. The code is publicly available at the GitHub link shared here. Any other questions? Feel free to ask. You can email me, and also thank you very much for your attention. I'm happy to take any questions. Here, let's see some of the figures. This is the gradient norm evolution over the 200 rounds on both datasets. The point is simple. All 4 stable methods, FedAvg, MB-LSGD, scaffold, and proc-skip, keep their gradient norms bounded throughout training. There is no explosion, and MB-LSGD's stability is comparable to scaffolds. FedCM is omitted from the plot because its gradient behavior is divergent. So the buffer feedback loop does not destabilize the optimization dynamics. And here are some other findings that we also can state here, that the intuition that says more participants should mean lower variance aggregates and better accuracy. So why did 10% beat both 5 and 20? 2 coupled effects, both specific to stateful methods, and neither of them is unresolved drift. First, our step size condition. Eta at most P alpha over 4LK tightens as P decreases. We held eta and alpha fixed across the sweep, so a learning rate that's admissible at one participation level can fall outside the valid range at another, and the per round dynamics shift exactly in the direction the bound predicts. Second, the participation rate changes how often each buffer is refreshed. The expected return interval moves from roughly 1 divided by 1 to P rounds toward every round, and the residual term 1 minus alpha over alpha P couples the two, so holding alpha fixed while varying P moves the tracking error floor non-monotonically. The bottom line is, once you retune eta and alpha for the target participation level, the dependence becomes monotone again, matching the standard intuition. It's a sensitivity of fixed hyperparameter sweep, not a flaw of the drift correction. Thanks for listening. Here are some of the references that I utilized in this presentation. Thanks.